these theory ideas could be examined through experiments. Then I hope we can cover the standard model, and I will comment on the important measurements we want to do with the standard model. Also, where is the place that we hope and have a chance to test the possible theory beyond the standard model. Okay, so the idea is that how we can produce this kind of kinematic measurement product. So because that's exactly what you can calculate using theory, and all of this distribution actually comes from this event display. The way that highly physics work is basically you build a huge camera, and you have learned this kind of analog. And this camera is just much more fancy that it's not just taking the geographical picture, but you can also generate the kinematic information from this object. So this is a cartoon about the detector complex. A modern detector, general purpose detector, looks like very similar to this. And you have the proton move and accelerate along the z coordinate along the beam pipe, and you try to collimate the beam so you can increase it in the center. So from the center, going outward through a detector, first you have a tracking device which can measure the trajectory of charged particles. And you apply the magnetic field, so from the curvature of the trajectory, you can measure the momentum of the charged particle. Then you put a calorimeter here, which can measure the energy of the either EM particle or the hadron particles. Then outside the calorimeter here, you put additional tracking device. So if you have muon, which is a minimum ionizing particle, you could use those devices to either tag the muon, or if you build more layer outside the calorimeter, you can also even measure its momentum. So I just have a brief through about how this cartoon of detector looks like. So my plan is trying to go through a little more detail of how each object is being detected and their basic working principle. Here is basically the same picture as the previous slide, except the previous slide I make a segment along the z direction of the beam pipe, and in this picture I make the segment along just face along the direction of the beam pipe. That this is sometimes we call R5 direction. So this is a phi azimuthal angle around the detector. So from the interaction point, and you have all these different kind of objects going out, and it's a little bit offensive, but basically when we talk about this in terms of the theory, you probably just need to keep in mind that if you want to convert your theory model to some phenomenological detectable object, so you can do some experimental predictions. You usually will just take the fallback of your object, and if it's a charged particles, and you convolute this fallback with intrinsic resolution of a tracker. So this is the typical resolution how you convolute the charged particles in the detector. And basically the resolution is proportional to the transverse momentum. So for the charged particle, if your momentum of particle is higher, the resolution just gets worse. And instead of charged particles, if you talk about some neutral particle, for example, photon, electron. So electron, you can convolute its charge component, or you can just look at its energy detected by calorimeter. Then, in that case, the resolution of the energy is inverse proportional to the square root of the energy. Okay, so in the typical resolution in a calorimeter is basically about this factor. Okay. All right. So I will try to go through each object in next slide. Before that, let's try to set some coordinate. In Hadron calorimeter, in Hadron Collider physics, we typically use the angular unit called rapidity. So it's defined this way, and the benefit to define rapidity is in the Hadron Collider. If you have a being going around a beam pipe, most of the system actually will be boosted along the z direction, right? So if you calculate your hard physics, usually you want to sit in the center of mass frame, because that is easier reference frame. You can generate Monte Carlo particles. Then once you generate the particles in the center mass system, and you can just boost into the left frame, so you can complete your Monte Carlo generation. And the boost is mostly along the z direction. Yeah, actually, in the Parton level calculation, you have no transverse momentum put into your photon system. So when you do the boost, you can see that the rapidity has a nice property. The Lorentz boost along the z direction becomes just an addition of the rapidity. Okay, this is nice. If you have two objects, they have rapidity difference in one number in the central base frame. And if you have the same boost to the left frame, you can see that the difference of the rapidity will be invariant quantity, no matter which frame you are. And these are very nice things. So once you try to calculate an observable based on the rapidity, and you have a multiple object, then the difference of this observable will preserve. Okay. So now, because we are working on extremely high energy collider, so if you take the high energy limit, basically almost all the final state particle, even the proton, you can approximate to be a massless particle when you calculate the rapidity. And we usually, instead of using rapidity, then we will do the pseudo rapidity, which make your all the calculation easier. So if you try to look at the relation between the pseudo rapidity and the polar angle, so theta is defined along the z-axis. This is your polar angle. So you can see a very nice correlation here. Okay. So you can also learn that if we talk about pseudo rapidity 0, that will basically means the theta angle 90 degrees. So it means you are thinking about the angle just perpendicular to the z-axis. Okay. So once we define this coordinator, later on when we talk about some other quantity, it will make more sense to you. Let's come back to the particle detection. Basically, all we care is how we can detect all these centimeter particles. And actually, you will see later, some particles you cannot detect directly because they are unstable particle. They decay to other lighter particle almost in the either QC time scale, if it's a QC or EHV time scale, but it's beyond what your detector can detect. So in the end, we will conclude that the way we detect all particle is actually trying to look at the almost stable minus a particle. So in terms of detection, here I list a nice timeline how different particles and when they were detected. So basically, now around the time of up to here, okay. So we have roughly 200 particles created observed at a time, and we actually did not have a full model to discriminate which one is a elementary particle or which one is a composite particle. But nowadays, we have a more clear picture. And the some people behind the detection instrumentation of paleophysics are listed here. These are the Nobel Prize laureates who invent the innovative instrumentation technology and move forward the paleophysics field. And we now all benefit from their invention. And one interesting thing is that if you look at the Atlas and OCMS, just go through all the different detected components, you will find a couple of inventions behind these people. So by 1959, there are 20 particles listed in the Paleo Data Group data sheet. So here, we list different particles discovered by all kinds of different detectors. So I would like to point out some of them. For example, cloud chamber. So cloud chamber is easy setup that if you try to put a chamber and just put some gas which try to get it reach to the saturated point, it could be just dry ice, which have a carbon dioxide. And then if you try to just put on the any place that you have accessible to cosmic ray, that is almost everywhere. And you can start seeing that some kind of tiny bubbles just created inside this chamber. So you can build this at home by yourself. If you haven't done that before, I encourage you to try that because all the material is less than $180. Yeah, and you can even. Huh?
You're talking about NT dollar.
NT dollar.
NT dollar.
Oh, sorry, US dollar. Yeah. US dollar. Yeah. But if you try to recycle some material, probably you can make it cheaper. Okay. So this is what I made. I sometimes bring it to some science festival to show to the kid that I can catch the fundamental particle in front of them. So this, if you put into some dark room, just cover with some dark cloth, and then use some fresh light. Just put it next to it. You can start seeing all those little bubbles show up here. So this is a very simple device, but when it was invented, it's not trivial. And it actually led to Nobel Prize. So for example, this cloud chamber led to the discovery of positron. It actually also led to the discovery of the cosmic muon. So it was almost 90 years ago that when Howard Anderson invented this device. Okay, so this is actually one of the first realization of how tracking device could happen. So underlying principle is that you have some molecule gas, and if you have a particle which have a chance to deposit sufficient energy to kick off the electron from the molecule. You ionize the object, then you have a chance to attract the nearby molecule to form some bubble due to the tensor surface of the bubble gas. So then muon is also discovered through that. And then I skipped some of the detector, but I would like to jump to the bubble chamber because this is another example that even you have a drink with your friend in a bar, there's a chance for you to invent a Nobel Prize instrumentation. So that's exactly how bubble chamber was invented. So we have a chamber in a similar spirit that if you have a big chamber and you put some liquid inside, and you have some piston trying to press the gas object, the liquid object here to some saturated point. Then when the particle goes through that, it could have a chance to leave the trajectory, and you can use the piston to control different saturation point of the gas. So you can keep the trajectory or refresh the trajectory to wait for the next event. So this is actually, this invention have a chance to make it be huge. So from the 1954 to roughly 20 years development, you can see that it evolved from a small 6 centimeter chamber on the tabletop, then it become a huge device, like 1 floor large. So I'm not sure I have a picture. Sorry, I did not put a picture, but if you have a chance to visit CERN, and next to the CERN cafeteria, you can see a chamber, looks like a space, capsule things. Like, and that's one of the historical bubble chamber that now become a museum exhibition. But this drive the movement of hydrogen physics for 20 years. Yeah. So it discovered all kind of subatomic particles. For example, omega baryon was discovered by that. So then we move on to the electronic revolution. So basically, what happened is that we have the invention of the particle detector, which try to take advantage of the burst of the semiconductor device, and also all the electronic component, fixed electronic component. So we have a Geiger counter and multiplier spark chambers, and this replaced the bubble chamber that instead of using the analog media to have detection of continuous spectrum trajectory of particle. Now you can try to use the electronic device to digitize your data, and then you can start using the digitization processing to process all this large amount of data. Then this is a key invention that allow you to be able to bring the particle production and also the detection rate to a very high speed. So this is a picture about the spark chamber that it was developed in the early 60s, and this is some just the schematic show how they work. And the spark chamber and have a chance that you can build really huge. Okay, so basically you have the singular layer that put in this layer structure. So you will have the particle go through that. They have generated a scintillation light, and the light was trigger some high voltage pulse between the metal plate and those sparks could be detected using some the ADC device. Then you can detect the data and identify which plane actually get the fire. And then if you connect the trajectory of those plane, then you get the reconstruct trajectory of the charge particle. So then the spark chamber have some limitations, and their improvement of the invention of the multi-wire proportional chamber. So basically, what you do is that it's a similar idea. You want to detect the ionization particles. So what you can do is that you can fill the chamber and you put a lot of wire, thin wire in parallel. So if you have a particle go through this chamber, and along the trajectory, you can create the trajectory of the ionized molecule. And if you apply the electric field on those sense wire, then your electron and the molecule, ionized molecule, will be drifted to anode and cathode separately. Then you can try to see which wire get fired, and you know where the particle goes through. This proportional field chamber led to a discovery of the W boson, Z boson in 1983. And this is the event display of how the Z boson was detected. You can see that there are two energetic charged particles go through that, and they are identified as a muon. So then we move on from the gas detector to the semiconductor detector, the silicon detector. This is the first application of the silicon detector to high physics, which led to the discovery of top quark in Tevatron. So the silicon detector is crucial in a way that now if you try to produce your collection data in a higher speed, so not only that, you increase the energy of the particle collisions, then the number of particles produced per collision become relatively large. So if you still use the gas chamber, you generate ionized molecule, but before they recombine to ready for take the next signal with an ambiguity event, and the next collision already come here. So then in that case, you basically will saturate all your detector. You cannot really separate which one is fire or which one is not fire. And silicon detector is a relatively fast device, so you will not have such issue. The other thing is that silicon detector, you have an opportunity to make the pitch distance between different sense very, very small. So you can detect the trajectory, measure the spatial position to a very high precision level. And one thing is that if you have the heavy quark, which is bottom quark produced, it has a relatively long lifetime. It could produce in the collision point and drift to some distance, about 1 meter, in Tevatron energy. Then it decay here. So you want a device that can reconstruct this secondary vertex, and silicon detector become the only option you have. Okay. So I would like to briefly summarize. So actually, the particle we just talked about here, they have one major feature. They are all so-called stable particles. Stable is actually a relative concept. Stable just means that their lifetime is greater than 500 micrometer. So with this, actually, when you produce those particles, and if you calculate their speed, it's quite close to speed of light. So if you multiply by 500 micrometer with this speed of light speed, you can see that this kind of particle from their production point to where they possible to decay, they can traverse quite a long distance, greater than 10 meters or more, greater than 50 meters. So that means if you produce a detector within that 50-meter size, you can basically see all these particles from the center to all the way across the detector. That's why we define it as a so-called stable. So what are those subparticles? Electrons and muons, photons. These are the typical particles we are quite familiar. And then actually pion tail. These are particles that we can also detect them and consider to be stable particles. So for this particle, what we are interested in, we are interested in if you have particles, how could I discriminate them from one to the other? What's their mass? What's their charge? And the important thing to separate, to identify what kind of radiation particle it is we need to understand their interactions. So the interactions of these particles, we can briefly summarize to 3 categories. So let's talk about the first one, photon and the matter. So the interaction between the photon and the typical media, we have learned quite familiar with that. Actually, also is a standard practice in when you learn 3D. So when you have the photon, which interact with electron, and the way possibly could happen is that if the photon have sufficient energy, that it could kick off the electron from the molecule. Okay, so or if your photon has sufficient energy, which is greater than mass of the 2 electrons, then you can create a process called the pair production. Yeah. So once you have defined the interaction between the photon and the electrons, this ionizing process and this complex scattering process and the pair production process, and we will try to see how about the electron interaction with the matter. So the electron have when it's low energy. So when you interact with this of the matter which have this kind of atomic structure, so it could interact mostly through the ionization as well. And however, if the electron have a relative higher energy, and if it have a chance to go very close to the nuclear, because of the Coulomb force, it could experience quite a large kink. And with this large acceleration, and we know that there will be energy released through the brainstorm radiation. So electron can actually, with a high energy, but it can radiate a high energy photon and then lose the energy. Okay? So if you think about the energetic photon, it could generate pair of the electron. And when the electron have a high energy, it can undergo brainstorm, produce a photon. Then you can imagine that when you have a photon come into some material,